Okay, all right. So let us begin today's session. This is session number 6 and this session is for solving the assignment number 7. So in the previous class we were looking into the problem of reliability models for power distribution networks, and we have also seen problems based on the reliability indices for power distribution networks. And in today's session, we are going to solve problems based on the power flow analysis in the power distribution network. So as we all know that power distribution networks are of radial in nature. So there are many power flow analysis methods for these distribution networks, but one of the most common and widely known method that is known as back forward and backward sweep load flow algorithm that we have it has been covered in this course. So in this forward and backward sweep load flow algorithm, we were going to solve the problems. So let us see the steps for flow analysis of radial distribution networks. So first step is that draw single line diagram for a typical distribution network. And after drawing, if it means in the problem you are given with the distribution network and you have to make the single line diagram. And we all know that we can make the single line diagram for the balance system only. So this method is for balance system only. And then after making the single line diagram, then prepare the data file like node data and line data. And this one is for the node data. This one is node data. So there are different nodes after making single line diagram. So we treat the first node as the select node or substation node.
Good evening, sir.
Yeah, good evening. So we were here. Here we are given with we have to we are looking into the steps for load flow analysis. So we the first node we treat at it as slack node or substation node. So that's why we have noted down the type like for slack node we treated it as 1 and 0 is denoted for load nodes. So so for slack node or substation node we are given with the voltage and angle, voltage magnitude and the phase angle for the voltage it is given in the problem, and then this active power and reactive power is unknown, and then we are having the load nodes that is between second number node and third number nodes, and we denote it as 0 since it is load node, and these are voltage magnitude and phase angle are unknowns for these load nodes. And what are the known quantities? Known quantities are this active power demand and reactive power demand at respective nodes or bus. So these are load nodes. And after preparing this data file for nodes, various nodes and or buses, then we prepare for the line data. And for lines, what are the values given? We are given with the resistance and reactance for the lines, and we represent it like what are the sending in nodes and what are the receiving nodes. Since this sending in node is 1 and receiving in node is 2, so the line connected between 1 and 2, so the resistance and reactance for this line is represented as R12 and X12. And after preparing this line data, then we convert all the quantities to per unit quantities on a appropriate base quantities. Like we take the base kV as the voltage value for this like node or substation node, and the power base power quantity we take it as the rated value of transformer, that is this substation transformer. Whatever, accordingly we choose this appropriate base quantities. It may given in the problem, otherwise you can take the according to the rating of transformer. And then we start for the load power flow algorithm. So there are various power flow algorithm for radial distribution networks. But in this course, it has been covered forward the widely known load flow algorithm, that is forward and backward sweep load flow algorithm. And what are the steps for forward and backward sweep load flow algorithm? There are three steps. In first steps, we calculate the current of each load. And how we can calculate the current? From this expression. We know that apparent power is equal to V into I conjugate. From there, if you take again conjugate of this, then it becomes V conjugate I. So it is S is equal to Vi conjugate, that means P plus JQ. And if you take conjugate of power, apparent power, then it becomes P minus JQ. And from here, you can write the current of each load, P minus JQ divided upon V conjugate for the respective nodes. And then after calculating the current, because all the values we are given, since the we assume the load as the constant power loads, so these P and Q values are unknown. P and Q value are known. And then this we assume as the voltage at different nodes, we assume at the starting of the load flow algorithm. And after knowing this current of load current at different bus, we go for calculation of line current, and that starts from the end of the feeder. That's why it is called like the backward sweep, because we starts from the last node, that is from the in nodes or terminal node. And after finding the line current, we calculate the voltage of each bus node starting from the first bus. So that's why it is called as forward sweep. Since the voltage value at the slack bus is known, therefore we can find the voltage from the starting from the slack node or substation node. And so these are three steps for forward and backward sweep load flow algorithm. Now let us see some important points related to this forward and backward sweep load flow algorithm. The assumption, but there are various assumptions. The first assumption is that unidirectional flow of power. So it is basically for radial, the distribution network which are radial in nature. If there is certain mesh or loop, then this forward and backward load flow diagram is not valid. And the second one is that this three-phase radial distribution networks are should be balanced so that we can represent by their equivalent single line diagram. And if, with the help of this forward and backward sweep load flow rhythm, we can determine both voltage profile and power loss of network. Since these are voltage profile at different nodes are unknown, so we are going to find the known quantities with the help of forward and backward sweep load flow rhythm. And in backward sweep, uh, so so first we are going to find the line current with the help of backward sweep, and then we are going to find the node voltage that are getting updated by the forward sweep. So if you see the important points regarding for backward sweep and forward sweep, in backward sweep we determine the branch or line current, and it is application of KCL, Kirchhoff's current law, and this computation starts with the in nodes or terminal nodes, and it requires more computation than the forward sweep. Why it requires more computation than forward sweep? Anyone can tell? If anyone is knowing this, why backward sweep would require no more computation than forward sweep? Till here, any doubt or anything? You can ask me. Dharmender, Jaswant, Lekha, Priyadarshini, Rahul. I think many one are just coming for attendance and they just left. So in the backward suit, first we compute the load current and then we find the line current. So it requires two expressions. That's why it needs more computation than the forward sweep. So this is the reason. Since in backward sweep we find first the load current, and with the help of load current we find the line current. So there are two expressions involved in the backward shift, so it requires more computation than the forward shift. And with the help of forward shift, we determine the bus voltage, and it is application of Kirchhoff's voltage law. And this in this computation starts from the slack node, that is basically the first node. So that's why it is called as forward shift. And this is expression for finding the voltage value at different buses. Now coming to the problems. So this is the first problem. The first problem that what is are the termination criteria for forward backward sweep load flow algorithm. And the options are active power mismatch, reactive power mismatch. C option is maximum number of iteration, and D option is maximum node voltage error between an iteration and previous iteration. So this problem is multiple select question. More than one options are correct. So type your answer in the chat box if you know the answer.
Uh,
Yes.
so is option C and D, maximum number of iteration and maximum node voltage error between an iteration and previous iteration?
Yeah, correct. Rahul Patel, you are correct. Just one thing, C and D is correct. So C and D both are correct. Transmission criteria for forward backward sweep load flow algorithm is that either to set maximum number of iterations which need to be exceeded, and this error in node voltage from previous iteration to current iteration, that is measure of convergence. And for a certain iteration, like we got the updated values v2 iteration, v3 and vn values, and now you have to find the error. And how you will find the error? Like maximum of, just subtract the values that you got from the previous value, with the previous values. So it is the updated values and the older value. So whatever the maximum of value you are getting, that is the error. And if this error is less than tolerance or accuracy, then you can terminate the program. So these are the two termination criteria for forward backward sweep load flow algorithm. Now coming to the second problem, in the forward backward sweep load flow algorithm, backward and forward sweep steps are associated with. So option A, it is single choice question. So single option is correct. You can type your answer in chat box. So first option is that calculation of node voltage and calculation of branch current respectively. And B option is calculation of active power and calculation of reactive power respectively. C option is calculation of reactive power and calculation of active power respectively. And D option is calculation of branch current and calculation of node voltage respectively.
Option D.
Yes, correct. Very good. Calculation of branch current and calculation of node voltage respectively. So with the help of backward shift, we calculate the branch current, and with the help of forward shift, we calculate the node voltage. And we do first the backward shift and then forward shift. So backward shift is for determining the branch current and forward shift is for determining the bus voltage. Now let us come to the next problem. Question number 3. In this problem, which of the following is are true for backward sweep a step in forward and backward sweep load flow algorithm? Again, it is multiple select question. In this assignment, there are so many multiple select problems. And the options are used for calculation of branch current. Computation starts with the most distance node. Needs more computation. Computation start with the slack node. It is asking about the backward sweep. So which of these options are correct for the backward sweep? You can type your answer in chat box. And if you face any doubt, then you can tell me. You can ask. A and C. Dharmender Singh, Rahul Patil. So yes, you are partially correct. So first option is that used for calculation of branch current. Yes, it is true. It is used for calculation of branch current. And B option is that computation starts from the most distance node. Yes, it is also true. Since it is backward sweep, then you have to start from the most distant node. That is also end node or terminal node. C option is that it requires more computation. Yes, backward sweep require more computation because since it involves two expression. And D option is that computation starts with the slack node. This is incorrect. And this computation starts from the most distance node. So A, B, C, three options are correct for backward shift. And here I have noted down the backward shift was determining the branch current or line current, and it is the application of Kirchhoff's current law. Computation starts with the end nodes or terminal nodes, and it needs more computation. Now moving forward to the next problem. So in this problem, you have to tell about the which of the following is a true for forward sweep in forward backward sweep load flow algorithm. So it is just same as previous problem, and options are same. So I don't think there is so much problem in this question. Since AB and ABC are correct for the backward sweep, so D is the only choice. So in the forward sweep, computation starts with the slack node. With the help of forward sweep, we determine the bus voltage. It is application of Kirchhoff's voltage law, and this computation starts with the slack node. Till here, any doubt, anything, any concern? So now moving to the next problem. In this problem, it is given that a distribution line has a resistance of 1.75 ohm and a reactance of 1.35 ohm. Consider base kV as 11 kV and base MVA as 100 MVA. The per unit values of the reactance and resistance are respectively. You can type your answer in the chat box. This is also simple problem. I think this assignment is one of the easiest assignment. Given resistance value as 1.75 ohm and reactance value as 1.35 ohm, base kV as 11 kV and base MVA as 100 MVA. So first we have to find the per unit values of resistance and reactance. Therefore first we find the base impedance. We know that base impedance is kV base square upon MVA base. So this is the base impedance value. kV base is 11 kV squared upon 100 MVA. Therefore it is coming as 1.21 ohm. Now we have to find the per unit values. So R per unit will be actual value divided by base value, R upon Z base. So R is 1.75 ohm and base value is 1.21. So it is coming as 1.446 and X per unit is X upon Z base. X is given as 1.35 and Z base is 1.21. So it is coming as 1.116. So in the problem it is asking that reactance first and resistance then resistance. So reactance is 1.116 and resistance is 1.446. Therefore C option is correct. Yeah, just one thing. You are correct.
I have given reverse.
Okay, no problem. It is simple. You may do mistake at This is common mistake we used to do in the exam also. Even in the GATE exam, after getting the correct answer, we may put the, if we don't read the question carefully, then we don't get any mark. Now let us move to the next problem. So this problem is that theoretical type problem. The first problem, sixth number problem, is that the basic principle of forward backward sweep load flow algorithm is based on the following assumption. And the options are bidirectional flow power, unidirectional flow power, both unidirectional flow power and bidirectional flow power, neither unidirectional flow power nor bidirectional flow power. So what do you think, which option is correct? Yes, Dharmender Singh, Jaswant Singh, Lekha, all of you are correct. Unidirectional flow of power. So B option is correct. Unidirectional flow of power. Moving to the next problem. From the results of forward backward sweep load flow algorithm, one can determine the following. Options are only voltage profile of a network, only power loss of a network. C option is neither voltage profile nor power loss of a network. And D option is both voltage profile and power loss of a network. So what should be the correct answer? Yes, D is correct. Just one thing, Rahul Patil. Both of you are correct. D option is correct. Both voltage profile and power loss of network we can determine using the forward backward sweep load flow algorithm. So moving forward to the next problem. So this is numerical type, and in this problem common data is given for question 8 to question 10. So a balanced radial distribution system has three nodes named as PQR excluding the substation node. So node P is nearest to the substation, whereas node R is the furthest from the substation. Node Q is located in between node P and R. This is all information about the node location. Till here, this is your information node location. Now, the load connected to the node R is having real and reactive power demand of 90 kilowatt, 50 kVA respectively. And the load connected to node P consumes real and reactive power equal to 50 kilowatt and 30 kVA respectively. And load connected to node Q demands real and reactive power equal to 30 kilowatt and 20 kVA respectively. Assume the base VA equal to 1 MVA and base KV equal to 10 kV and the initial gas value of voltage at the different nodes is 1 per unit. So determine the current drawn by the load at node Q in per unit at the first iteration forward backward sweep load flow. So let us make the diagram from the data. So in this problem the diagram is not given. So first we have to make the diagram with the help of data. So this is substation node or slack node. First we make the substation node or slack node, and then so let us take it as one node, and then this slack node is connected to the node P. So this is node P. So first node is P, and then P is nearest to the substation. So that's why This node is connected to the substation node, and node R is furthest from the substation, and node Q is located within the P and R nodes. So then we are having Q node, and then at the end we are having node R. So this is for the diagram. We make the radial distribution system, balanced radial distribution system, single line diagram for balanced radial distribution system. Now from the problem, it is given about the loads at different nodes. So load at node P, it is given as 50 kilowatt. So whenever the question is given, you have to first make the single line diagram. So it is 50 kilowatt and 30 kVR at node P. And then at node Q, it is 30 kilowatt and 20 kVR. And at node R, it is 90 kilowatt and 50 kVR. You may write in terms of kVA 50 plus J30 kVA 30 plus J20 kVA and then 90 plus J50 kVA. So now we have made the first thing for the load flow analysis, that we have to make the single line diagram with the given values. And now we have to find the current drawn by the load at node Q. For that, in per unit in per unit we have to find the load current. So take it as this current as denote this current as IQ, and this current as IR, and this current as IP, that are load current. And we can represent the line current like this is IQR, the current flowing from the Q to R, and then this is the IPQ, and this is the ISP. So you may take this, denote this slack node as S. And in this problem, the base value is also given. So base VA equal to 1 MVA and base KV equal to 10 kV. So they have to provide this base value also, since they are providing the options. So MVA base are 1 MVA and KV base as 10 kV. So now we have to find the load at node Q. So first we convert these quantities, power quantities in per unit quantities. So PQ power at, so directly we can write no, PQ per unit, that is PQ divided by MVA base. PQ is 30 and MVA base is 1 MVA, 30 kilowatt, and this is 1 MVA. So it will come as 0.03. And now this reactive power in per unit at the node Q So it is 20 kVAR divided by 1 MVA. So it is coming at 0.02. So we have find the power in per unit value and then we use this expression. We know that current expression for load current IQ is will become PQ per unit minus JQ per unit divided by VQ star conjugate per unit. So we know the quantities 0.03 minus J 0.02 upon 1 because the initial guess value of voltages are given as 1 per unit. So we have to take the initial guess at each node. So we have assumed the voltage at different node as 1 per unit. So therefore the current drawn by the load at node Q in per unit will be 0.03 minus J 0.02 per unit. Therefore option D is correct. How many of you got the correct answer? Yes, just one thing, Rahul Patil. I think this is a previous problem. This is also a very simple problem. I think many of you are able to solve this problem. If you have any doubt in this problem, we can discuss. Now for the same data, we have to find the current flowing in the line connecting node P and node Q in per unit at the first iteration. So this is the diagram. We have to find the this current IPQ. So how we can find the IPQ? We know this load current IQ. So we have to determine this load current IR also. So that we know that IPQ is IQ plus IR. So first we have to find the load current IR, then we can find the line current IPQ. So in this problem we have to find the line current IPQ. So therefore first we going to find the so IPQ. It's better to write IPQ is IQ plus IR. Since we know this quantity IQ and therefore we need to know this also quantity IR. So first we are going to find this IR value. For for load current IR, first we convert the power quantities in per unit. So PR per unit is PR upon MVA base. PR is given as 90 kilowatt. Whoever is getting the answer, type your answer in chat box. And MVA base is 1 MVA. So it becomes 0.09. And then QR reactive power in per unit will be QR upon MVA base. So QR is 50 kVAR upon 1 MVA. So you will get 0.05. Now we can find the load current IR in per unit. So it will be PR per unit minus JQR per unit upon VR per unit conjugate. 0.09 minus J 0.05, and initial value at different buses is 1 per unit. So it is 1 at the angle of 0. So it will same 0.09 minus J 0.05 per unit. Now we substitute this IR value so that we can get the line current IPQ. So IPQ will be IQ we know, IQ we have found. IQ is coming at 0.03 minus J 0.02. So IQ is 0.03 minus J 0.02 plus IR is 0.09 minus J 0.05. Therefore, it will become 0.12 minus J 0.07 per unit. Therefore, correct answer is B. You all note down this value. We require this value in the last problem. Yes, B is the correct answer. This one thing, Lekha, both of you are correct. And now moving to the this common data for problem number 10. So in this problem, the last step for any load flow algorithm is that we have to determine the voltage. So in this problem, it is asking about the voltage. We have to determine the voltage at node P in per unit at the first iteration of forward backward load flow, and impedance of the line connecting substation and P is given as 0.5 plus J 0.25 ohm. So let us see the diagram. So we have to find the voltage at P, and for finding the voltage at P, we have to find the total current ISP. How we can find the ISP? Line current flowing from the substation node to the node P, that is equal to the total load currents. Total load current is IP plus IQ plus IR. Since we have find the load current at node Q and node R, so now in this problem we have to first find the load current at node P, and then we can find the line current ISP, and we are given with this slack bus voltage, that is 1 at the angle of 0, and we are also given with the impedance of this line. Then we can find the voltage magnitude at P. So therefore first we are going to find the load current at P. So I am writing directly, since P value is given as 50 kilowatt and QP value is given as 30 kVAr. So in per unit quantities, it will become 0.05 per unit, and QP become 0.03 per unit. Now we can find the load current at node P. So IP is PP per unit minus J QP per unit upon VP per unit, VP conjugate per unit. So it will become 0.05 minus J 0.03 per unit. So this is the load current at node P. So total load current is flowing through this that flowing between substation node and the node P ISP. So IP plus IQ plus IR. If you do solution, then you will get 0.17 minus J 0.10 per unit. Okay, so this value we got. Now we are given the impedance of the line connected with node Pn between the substation and node P. So this value is given ZSP. ZSP, this is substation node and this is P node and this is current ISP. ZSP is given as 0.5 plus J 0.25 ohm. So we have found this ISP in per unit. So let us find the ZSP there. So first we are going to find the base value. So Z base is kVA square, kV base square upon MVA base. So kV base is 10, kVA square is 100 and MVA base is 1. So it is 100 ohm. Therefore we can write the impedance value connected between substation node and P node in per unit as ZSP upon ZB. ZSP is 0.5 plus J 0.25 upon Z base is 100. So it will become 0.005 plus J 0.0025 per unit. Now it is simple. We have to apply the KVL that comes under this forward shift. So we know this voltage at slack bus and we are going to find the voltage at node P. So we are moving forward. So it is comes under the forward shift. So voltage at P equal to voltage at S minus, so voltage at P equal to voltage at S plus volt minus ISP into RSP per unit plus JXP per unit. So all values are in per unit. We have to just substitute all the values. So Vp equal to 1 minus ISP 0.17 minus 0.10, RSP 0.005 plus J 0.0025. You will get Vp as 0.9989 minus 0.00075 per unit. So voltage at point P is after first station at the first 0.9989 minus 0.00075 per unit. So you have in this problem we have to ask about the real part of voltage. Hence real part will be real part of voltage at P is 0.9989. Therefore C is the correct answer. How many of you got this answer? Yes, Lekha, you are correct. Very good. C is the correct answer. Now we move to the next session. So I am giving you the link. Kindly join by this link. Sorry for this inconvenience. So I am sharing one link in the chat box. You kindly all of you join by this link. 1 minute it is. I think internet is a little bit slow. Okay, all right. So I am sharing this screen. I hope you are able to see the screen. I think Lekha didn't able to join. I am always having this same link, so you can, if you missed this, so you kindly save this link and you can join anytime. Okay, she also came. Okay, we have completed 10 problems. Now we move to the next problem. So let us see this 11 problem. This is very simple. Just we move fast and complete it in. I think we have 10 more question. Become just it is revision. So we will complete it very fast. In this problem, it is same. We have to find the per unit resistance, base value, MVA values, and the resistance value all are given. So first we find this Z base. We know that it is kV base square upon MVA base. So kV base is given 11 square and MVA base is given as 100. So it is 1.21 ohm, and we have to find the R per unit. So 1 point actual value is 1.5 ohm and base value is 1.21. So it is coming as 1.24. Therefore, A is the correct answer. You also solve it quickly. We have some good question there. Yes, 1.24. Moving to the next problem. Here the quantity is given in per unit quantity. You have to find in ohm value. So actual value is x per unit into base value z base. So x per unit is 0.5 and z base we have computed previously, it is 1.21 ohm. So it is giving it will give you 0.605 ohm. Therefore D is the correct answer. Yes, Jaswant, Rahul, Priyadarshini, all of you are correct. And then next problem. In this problem, you have to tell about that. This is theoretical type question. Which of the following is correct statement in view of sequential iterative steps performed in forward backward shift load flow algorithm? So what things we calculate first and then we perform? Options are: firstly, line currents are updated in forward sweep and then node voltages are updated in backward sweep. B option is: firstly, line currents are updated in backward sweep and then node voltages are updated in forward sweep. C option is firstly node voltages are updated in forward shift and then line currents are updated in backward shift. And D option is firstly node voltage are updated in for backward shift and then line currents are updated in forward shift. So what do you think? Which should be correct option?
Option B.
Yes, correct. Option B is correct. Line currents are updated using the backward shift method and then node voltage are updated in forward shift. And moving to the 14th problem, the forward backward shift load flow algorithm starts with the guess value of. So options are node voltage of load nodes, B option is node voltage of slack node, C option is load currents of load nodes, and load currents of slack node. So what should be the correct answer? Anyone know the answer for this problem?
Option B.
Node voltage of slack mode.
No, no, you got it wrong. The slack node voltage is given in the problem because if you see the substation means voltage is defined using this distribution, sorry, the substation transformer. So the voltage value we are given. So based on this per unit quantities, they just give it in the value, give it in the problem. Slack node means what? Slack node means like voltage and phase angle are known. Even in transmission system, this is same. Known, these are known quantities. So we don't assume the voltage value at the slack node. These are known quantities. Voltage and phase angle are known quantities.
Node voltage of load node.
Yeah, A is correct option. These are known quantities. Unknown quantities are P and Q. After finding this, all the current values means whatever the you can find the P and Q from the that is supplying from the select node also. So A option is correct. Node voltage of load nodes. Select node it is defined. These are known quantities. So we don't take any guess value for the select node. We take the guess value of load nodes and in the subsequent iteration and based on the termination criteria you will get the final answer for the node voltage at the load nodes. So this problem A is the correct answer. Sorry. Okay, I will do it later. So this is the step flow chart for backward forward sweep approach, and you can refer to the lecture notes. Now coming to the next problem, which of the following steps needs more computation? Forward sweep, backward sweep, lateral sweep, downward sweep. So what should be the correct option?
Backward sweep.
Yeah, backward sweep. Because in backward sweep, we have to first find the load current, and with the help of load current, then we find this line current. So these two expression involved. While in forward sweep, you have to just apply the KVL, and in the backward sweep, we apply two expression. One is the power expression, and one is this KCL. So this backward sweep requires more computation. Now moving to the next problem, the following parameters are specified for load nodes of radial distribution networks: active and active power, voltage magnitude, voltage angle, power loss.
Active and reactive power.
Yeah, similar to like transmission, whatever we study in the uh, various load flow algorithm for transmission system like Newton-Raphson load flow algorithm, Gauss-Seidel load flow algorithm. There we define the load bus as the PQ bus where active and reactive power is specified. Similar here for load nodes, we are active and reactive power is specified, and we also treat the load as the constant power loads. So that means active and reactive power are specified. Now moving to the next problem. So in this problem, the power demands of a node for a radial distribution network are 80 kilowatt and 60 kVAr, and the base volt ampere is 1 MVA. Determine the current drawn by the load in per unit to be computed at the first iteration of forward backward sweep load flow approach. So it is the fund we have to apply this load current expression. Power demands are given as 80 kilowatt and 60 kVAr. MVA base is given as 1 MVA. So first we find this power in per unit. So it take 80 divided by 80 kilowatt divided by 1 MVA. So it will give you 0.08 per unit, and Q per unit it is 60 kVAr divided by 1 MVA. So it is 0.06 per unit. And we know that what is the current expression, load current expression, that is P minus, it will become P per unit minus JQ per unit upon V conjugate. So P per unit is 0.08 minus J 0.06, and voltage magnitude, take the initial guess as 1 per unit. If it is not given in the problem, you have to assume this 1 per unit. So the answer will be 0.08 minus J 0.06 per unit. Here you can, therefore D is the correct answer. Here you can write this point. The guess value of voltage at the first iteration be 1 per unit. So how many of you give the correct answer? D is the correct answer. I think it's just one thing has given the correct answer. So D is the correct answer. Now moving to the next problem. So what are the data of distribution lines required to perform the forward backward sweep load flow algorithm? You have to, what data are given for the data of distribution lines are given for performing the forward backward sweep load flow algorithm, and it is multiple select question.
Line resistance, line reactance.
Yes, A and B are correct answer. After knowing the line current, how you can find the voltage at different buses with the help of this line resistance and line reactance by applying the KVL. So A and B are the correct option. Now moving to the next problem. The computation of forward sweep of the forward backward sweep load flow algorithm starts with. So I think we have discussed this problem. So forward sweep, where it starts, Substation node, most distance node.
Slack node.
Yes,
Substation node, slack node.
yes, B is the correct answer. Now the last problem. The computation of backward sweep of the forward backward sweep load flow rhythm starts with
Option
The
A, most
most
distant node.
distance node.
yes, most distance node. Beyond which there is no need. So backward sweep means backward direction. Backward sweep means you have to start from the last node and you have to travel in the backward direction. And for forward sweep, you have to go in the forward direction. So I think that's all for today's session. If you have to discuss anything related to any part today's session and previous session, you can ask. We have still more time. So this assignment is quite simple. Means you have to just read about forward backward sweep load flow rhythm and it is quite easy, not that much complex. And we apply this load flow rhythm in radial distribution network, and radial distribution network has many advantages, like we have proper coordination and we don't have to invest too much on protection system. Okay, thank you everyone. If there is no concern, we can close today's session. Thank you everyone. Have a good dinner and good night. Okay, bye.